Emissions Discussion Group. Firstly, we would like to acknowledge that we're meeting on the land of the Kulin Nations and pay our respects to their elders, past and present. We'd also like to thank the University of Melbourne Energy Institute, our Zero Carbon Australia project partners, for this great venue. For anyone that hasn't been to one of our discussion groups before, VZE is a climate solutions think tank and research organisation. Our goal is to transform Australia from a 19th century fossil fuel-based economy to a 21st century renewable powered clean tech economy. Our projects include Zero Carbon Australia research, Repower Australia talks, media work, education programs and much more. We're always looking for more volunteers, so come and talk to us afterwards if you'd like to get involved. The discussion group is a forum for climate change solutions with presentations by experts in their field and is held on the first Monday of every month. After a very successful Melbourne launch of VZE's electric vehicle report last week, we're pleased to welcome back Michael Lord. Michael is the lead researcher at VZE and currently the acting CEO. He's an environmental analyst and campaigner with 15 years experience of developing strategies across a variety of industries, focusing on climate change policy and projects in the UK and Australia. Tonight, Michael is discussing some initial findings from his research into emissions reductions in industrial processes. The Zero Carbon Australia Industrial Processes Plan is the next report in VZE's Zero Carbon Australia project, which aims to decarbonise each sector of the economy in 10 years using currently available technology. Would you please welcome Michael?
Thank you, Hugh. This is going to be, for a couple of reasons, definitely a discussion rather than a fluent presentation tonight, because we're still at the early stages, really, of this report. As you said, I came on as lead researcher, but I've never really been able to focus all of my time on this, especially since I've been acting CEO. So what I'm going to do is, my plan at the moment for this report is in 4 different sections. So I suggest I'm going to talk about what the plan is for each of the sections, and then we'll have questions and discussion at the end of each of those sections. So industry, it's the last big area, really, the last big emitting sector that VZE hasn't looked at yet. It's about 12% of emissions in Australia. So about half of those are from the direct energy requirements of industry, half of the emissions, and the other half are from process emissions from chemical reactions required to produce industrial products. So when we're talking about industry, we're talking about industrial materials, so not kind of manufacturing of cars and computers and things. We're talking about the more initial materials like steel, other metals, plastics, chemicals, paper, things like that. So that's what we're dealing with in this report. And the emissions from industry are very rarely discussed in public policy. When the media and politicians talk about emissions, it's nearly always about electricity generation, a little bit about transport, buildings. It's very little about the production of plastics and things like that. So that's one thing this report can do, quite aside from presenting the solutions. It can raise awareness that part of the solution has to be to tackle emissions from industry. It's a pretty big area, so about a third of the world's energy is used for industry. If you divide it up into roughly a third for buildings, transport and industry. So it's a massive area, and it's about the same for the emissions. This report will also be a nice link to one of our most recent reports, which is the Renewable Energy Superpower report. So that report makes the case that we've got abundant renewable resources in Australia, and that gives us comparative advantage. And one of the reasons it gives us comparative advantage is that Australia is in the best position to produce energy-intensive goods like steel and aluminium in a low-carbon world. So there's a nice link to that report in the industry plan. These are the industrial products that lead to the most emissions production, and these figures have led me to one of the reasons to structure the report. It will go in depth into only two products, which are cement and steel, and that's because overwhelmingly they're the biggest ones. So these will be the four. Look at the four that aren't crossed out. These will be the four kind of areas that the report will go into. So renewable heat. So part of the problem of industry and emissions is that most industrial processes require a lot of heat. That's usually achieved through burning gas. The majority is through burning gas, also coal, electricity, etc. We'll go in depth into steel, alternative ways of producing steel, cement, and then what I'm calling at the moment using less. Using less steel and cement. We'll come on to more of that. What that means. I was thinking about having a chapter on refrigerants. It was a lower priority, but you may have seen that there's recently been added to the Montreal Protocol the main refrigerant greenhouse gas that was the HFCs, which were used to replace the CFCs, which were banned by the Montreal Protocol, have now been added. So there is a timeline now for elimination of HCFs and HCFs. Thank you. And developed countries like Australia will be eliminating them in the next few years. So we probably won't have a chapter on refrigerants now. So renewable heat, one way of thinking about it is that different types of industry require a different temperature range. So food, for example, is sort of not much more than 100. Papers up to 150. And then there's medium ones in the chemical industry. Sometimes it's up to 260, and then the highest would be things like cement. It's about 1,1300 degrees, and steel, and a couple of other things are more than 1,500 degrees. So, how do you achieve this heat renewably? One of the ways is our old friend solar thermal, concentrated solar thermal. So not concentrated solar thermal to generate electricity, but directly to generate heat, which I think is a lot more. It's a lot more efficient. You can, the sunlight to heat efficiency can be 75%. It's a lot more efficient than generating the electricity. And you can actually get any temperature you like with concentrated solar thermal, really. It just becomes, as this shows, more expensive the higher temperature you're trying to achieve. But this shows that it can be done at scale. So this is producing with trough technology. Heat temperatures of about 150 degrees. This is a 7 megawatt concentrated solar plant in Oman. They're building now a 1 gigawatt version, also in Oman. The only problem with this one is it's used to, what industry do you think it's used in? Gas production. So it's producing steam for gas. So, but it is a proof of concept that an industry that needs a reliable source of steam can use concentrated solar thermal on a very large scale. And obviously, as we all know, in Australia we've got similar conditions in a lot of Australia to somewhere like Oman. And this one's in a greenhouse because it's so dusty. And they're cleaned by, all the mirrors are cleaned by robots. I won't go into that yet. So that's CST, which will produce, in the right circumstances, can produce heat. but the main way of producing heat is going to have to be electrification of heat. I should have mentioned what we'll do about energy efficiency. Most reports, studies that look into how to reduce emissions from industry start with energy efficiency, and often they end with energy efficiency. They just say, oh, this is best practice in energy efficiency, this is where the industry is at globally, look at how much we could save with best practice, with technology improvements. After giving it some thought, I just don't think that's the way to go, because it's a little bit like the analogy with cars. You can make internal combustion engine cars more efficient and gradually improve standards, but we no longer have the luxury to wait for standards to gradually improve 3% a year. And why do it when we've got an electric vehicle which has zero tailpipe emissions? To me, it's the same thing with industry. Why make fossil fuel processes of generating heat more efficient when you could just do it with CST or electricity and get it down to zero emissions? And if we're talking about, and loads of people have studied energy efficiency in industry, and there's a slow curve that doesn't really get you very far, and nowhere near zero, even when you look out to 2060 or something like that, because you're still burning gas and coal to produce the heat. So yeah, electrification of heat will be the other big thing, and their energy efficiency will come into it, because one benefit of electrifying the heat is that you'll be able to target the heat a lot more specifically. You'll be able to target it a lot better. So electrification of heat will be one of the other strand to renewable heat. So that'll be the first section. So that's a kind of general section that'll be applicable across different industries. So what do people think? I'd be interested to what you think as to how we're planning to structure the report. So those 4 chapters and the approach to energy efficiency and renewable heat.
So your rationale is, there is an expression to knock off the low-hanging fruit, I guess, stretching the analogy a bit too far. And you think that the lesser industrial energy problems will sort of be dragged along by those major improvements. Is that sort of the way you see it? Say aluminium, for instance.
You haven't included it on that list.
I haven't included aluminium. Sorry?
You should have.
I should have, okay. I haven't included aluminium because, nearly all of the energy it requires is electrical. So it's less interesting for us to look at. I mean, basically we'll just be saying, this is how much electricity you need to produce aluminium, let's do it renewably. Which we've kind of already done before. It's not a big component when you compare it to steel and cement of emissions. And because you can produce renewable energy, we know electricity, we know how to do that. It's not really as difficult. Like in Iceland, they already produce zero emissions aluminium. Sorry, but yeah, I wouldn't describe it as a low-hanging fruit's usually about energy efficiency. So I wouldn't describe any of this as low-hanging fruit. In fact, I should preface all of this by saying we try and take off-the-shelf technologies at BZE. That's pretty difficult to do in some of these areas. Renewable heat is not too bad, but some of the others, it's pretty tough.
So maybe another way of stating it is that these, particularly steel and cement, are highly wedded to hydrocarbon energy sources. Well, I guess steel in particular, the most abundant reductant to turn that iron ore into iron and eventually steel is still hydrocarbon.
Yeah, we'll come into steel and cement in a minute, but yeah, there are bigger challenges to do with the chemical process. Yep. Sorry, you go.
Michael, is part of the issue that where there's abundance of renewable energy is miles of kilometres away from where the plants currently exist. It seems to me that, say, especially gas, you may need gas for a while. You really should have the industries that use them at the ports, where the gas is brought to, rather than along the gas corridor. You know, the State for Yellow Submarine, South Australia, may be the ideal place where you move these heavy industries to, which is away from population centres. Is that part of the complexities?
It is. It is. I suppose for CST, if you're electrifying heat, if we're just talking about heat at the moment, if you're electrifying heat, that doesn't matter so much because you can just transmit the electricity. But for CST, you need the plant next to exactly the right conditions. So it's not right for everywhere. You're right. But there's a nice fact that there's, for example, there's a lot of minerals, say in Western Australia, iron ore, that is in places where CST would work wonderfully.
So that what they export is not the raw iron or whatever. Is a refined product.
It could be steel or whatever.
Now then you're getting into all these horrible trade fights. The moment BHP gave away its industrial technology to Japan in the 60s. That's when that argument got lost. Like BHP had all those patents on refinement of steel, which it handed over to the Japanese steel manufacturers in the early 60s to buy their steel. To get a bank guarantee off Citibank, all works becomes that's where the whole problem starts to unravel.
So I'll just take another question. I think you're right.
We're even cover alternative materials like carbon fibre, for example, substitution, less use of cement. Is that going to be covered in this?
That'll be the using less chapter. Well, I'll get onto that in a bit. But that's right. Alternative materials will be part of it. The using less chapter in some ways is the most difficult sort of conceptually. But that'll be covered.
So you were assuming that you're going to build a concentrated solar plant next to the aluminium plant to be able to supply it, or are you going to ship it through the regular transmission lines where there's going to get losses through the lines?
The concentrated solar is for types of industry that need heat directly, so not for aluminium. Aluminium would be using electricity.
Well, you put a solar thermal plant to generate electricity next to the aluminium plant.
You could do. We won't be really going into that.
Just using the ordinary transmission lines to move electricity around.
Is there a role for cogeneration?
Not really. It wouldn't be part of this anyway, but in general I don't particularly see a role for cogeneration. No.
Can I just ask another one? If the majority of your energy is turned into electricity, and Alan Finkel speaks of the electric planet, it sounds right to me. I'm a bit worried about Alan Finkel's next proposition that we use gas as a bridging fuel. Perhaps, I don't know what he has in mind there, retrofitting electricity generating plants that are presently running on coal, I guess is what he has in mind. But he indicated that the transmission losses typically are about 7%. Now, Mother Nature long ago realised that if you have an abundant source of energy which is coming from a distant nuclear reactor way above our heads, photosynthesis, for instance, is, and maybe some of the more advanced plants use, when I say plants, I mean biological plants, are more efficient, but photosynthesis is always deemed to be about 1% efficient. But that doesn't matter if you have a copious energy source, to wit the sun, to provide vast excesses. And in a way, in Australia, we are, in my crude understanding, in roughly that position. So a vast amount of energy coming in. But if I don't know, there's a trade-off obviously between the cost of capturing it and distributing it. I mean, with the South Australian energy crisis, in part, did highlight our lack of interconnections between sources, and I think that was a feature of your first report, piece there. There was, some major interconnectors. Now the capital for that, I don't know whether that was frighteningly.
Well, we're probably getting a bit beyond the scope of this report now, but yeah, we've got loads of energy. The Renewable Energy Superpower report quantifies that. We've got an absolute abundance of energy, and that's just near existing transmission lines.
Sorry.
Yeah, quick one.
Look, what about products that are being made overseas that would become more attractive to make here, given the quality of the renewable silicon-based or glass? Can that be covered here?
I mean, there's going to be a link made in this report to the Renewable Energy Superpower report that makes that point. So, yes. So, the next one is cement. So cement is about 8% of world emissions, just on its own, cement. So you don't often hear that. We make absolutely massive quantities of cement. You see different figures, but 3 billion tonnes, you see, or 4 billion tonnes, vast quantities. There's no other product we make the same amount of as cement, and it's kind of a really difficult problem, because as this shows, half of the emissions in producing cement come from the energy. So cement is essentially making limestone into lime. So it's that equation over there, calcium carbonate into calcium oxide and releases carbon dioxide. So half the emissions come from that process reaction when you're making cement, which occurs at quite a high temperature. And you're not going to get around that. If you're going to make cement the way it's made, which is with limestone, it's going to have that chemical reaction, and it's going to be very highly emitting. So unless you go for carbon capture and storage, which I'm trying to avoid, you have to make cement another way. So cement is just something that holds together aggregate and sand, and it becomes super hard and durable, and super useful. It's super useful, which is why we make so much of it. I mean, all these products are super useful, and what's interesting is that about 100 years ago, 120 years ago, we basically made none of them. The processes for making most of our metals and cement and things were all invented in the 19th century. And now we make massive quantities, and they're just as important to our modern life as the fact that we burn fossil fuels and have cheap energy. So we need another way of making cement. And has anyone heard of geopolymer cements? A couple of people. So geopolymer cements have a completely different chemistry. They're not based on calcium, they're based on silicon and aluminium, but they do the same thing. They don't produce CO2 in their reaction. It's a low temperature reaction to make geopolymer cements. They're also called alkali activated cements. They have a very complicated chemistry that I couldn't explain. The only emissions really that come from them is that in one of the catalysts for the alkaline reactions to make geopolymer cement does emit CO2. But there is one of the foremost companies in the world that make geopolymer cement, and these photos are all the things that have been used where geopolymer cements have been used. One of the foremost companies in the world that has stacks of patents on geopolymer cement is in Victoria, a company called Zeobond, which makes Ecrete and some other patented cements. And it has, from what I'm told, it has pretty much all the properties of regular, when it becomes concrete, a regular concrete. It's durable, it's hard, etc. Under some circumstances, it's more durable, less, I think, acid resistant, more fire resistant, etc. Under some circumstances, it's less durable. But basically, it can be replaced in any structural situation. They've used it at Brisbane Airport for some of the aprons at Brisbane Airport. They're using it now in South Africa for wind turbine footings. But there are a number of barriers to its widespread implementation, and one of those barriers is, well, just that the construction industry is very conservative. Another is that the standards of concrete in this country and most places are about the composition. They're not performance-based standards. They're about, it needs to contain this much Portland cement, which is the cement made with limestone. And so these geopolymer cements would fail those standards. But they are, they're a huge opportunity in terms of reducing emissions. There is one big problem with them. Does anyone know what that is? The big problem with geopolymer cement is what they're made from at the moment. So they're made from steel slag, which falls out at the bottom of a iron blast furnace, and fly ash from coal-fired power stations. So, as our sustainable solution, they have a little bit of a drawback. So this Victorian company gets the fly ash from the black coal-fired power stations in New South Wales. In Europe, all fly ash is now used in Europe. So it's not even really a waste product. So all the fly ash in Europe from power stations is used in cements like this. And the way they're used at the moment is they're just mixed in with ordinary Portland cement. They're not used in 100% format. But from what I'm told, they could be. So so I think we've got an interim solution to cement, which is using geopolymer cements. But obviously it can only be interim because it relies on this fly ash. So we need to find other materials. Basically, you need materials with a high percentage of silicon and aluminium to create the right type of chemistry. And there are a range of things that are possible. For example, have you seen that byproduct of alumina production that's very red? It's called red mud. A load spilt into the Danube in Hungary a few years ago and killed the river. So it's a very toxic waste product from alumina industry. Obviously high in aluminium, high in silicon. That would be a potential alternative to the fly ash. There's all sorts of things, some agricultural wastes, rice husk ash, sugarcane bagasse ash, waste clays from mine sites. But this isn't how they're made at the moment, so it needs to be developed and we need to investigate it
You
more.
might be able to use hemp fibre in some of the reinforcement in the future.
The reinforcement will come. Will come onto So we've got to look into this more. It's a difficult one, but that's the plan at the moment. And then the long-term strategy would be just totally other sorts of cement. So you might have seen that people have developed in labs carbon-negative cements. So cements where their reaction absorbs carbon dioxide, and they even when there is in their buildings, they continue to absorb carbon dioxide, and it's actually making the building stronger as that's happening. So there's that potential. And because we make so much concrete, that would be able to draw down CO2 in the atmosphere if you're making 4 billion tonnes of concrete a year. But the problem with making 4 billion tonnes is that however you're going to replace limestone as your raw material, and there's lots of limestone around, it needs to be also abundant and cheap. So we might need to make the geopolymer cements of the future with different materials, red mud, waste, different types of clays, etc. So that's the plan for cement. And if we don't tackle cement, the way it's heading, because emissions from electricity are due to start declining. Cement will be about a quarter of world emissions by 2050. So it's 8% now, which is bad enough, but they'll be pretty much the biggest part of the problem by 2050.
So Michael, is it that we have to find alternative products instead of cement? I noticed that especially in Scandinavian countries, there's this aggressive use of treated timbers.
Yeah.
Going up to 8 stories above, I believe.
Yep.
And I think in China there are 20-story buildings.
You're right. I'll get onto that. Oh, I just wanted to show this picture because it's my most attractive slide this evening. So where's that?
In Rome.
In Rome. Yeah, it's the Pantheon. So why do you reckon I'm showing that?
22 feet of cement roof.
Yeah, that whole roof, which has been standing for quite a while now. So one of the questions people worry about with geopolymers is that, well, we don't have the experience, it might look great, but in 20 years is the building going to collapse? Well, this has been there 2,000 years, and that's actually a geopolymer cement. I don't think anyone's 100% sure of the chemistry, but they used ash from Mount Vesuvius to create that cement. So there you go.
Sorry? They used what?
Ash from Mount Vesuvius. So the Romans developed a geopolymer cement by accident, really, because Mount Vesuvius was thereby.
I've seen a road in Syria.
Yeah.
We went out to Damascus, I think, and the road just stopped about Box Hill.
Yeah.
15 feet wide.
Yeah.
And obviously made 2,000 years ago.
Yeah.
And it was absolutely, the edges were just totally perfect.
Yeah.
Like it was made yesterday.
Or was it made from cement? Concrete?
Cement,
Yeah, okay.
Yeah. Just stunning.
Yeah.
You wonder, well, they seem to know things we don't know.
Yeah. Yeah, that's right.
I think so.
Yeah. So there you go. It does work. And I think using less cement will have to be part of it, because I think it's going to be difficult to replace 3 or 4 billion tonnes, whatever it is, with a new material. But we've got a plan. And the good thing is, there's this company in Victoria who are really happy to help us with this research, who are one of the foremost companies. The CEO of the company, Yanni van der Venter, is a professor here as well, professor of chemistry. And he's been trying to push geopolymers for 20 years, but because it's so hard to get it into the construction industry, he's actually now going to form his own construction industry and just start building things with it, because nobody else will do it. Any other questions on cement?
Of course, understanding the details, and as you say, the chemistry of a quick look at Wikipedia recently, that conventional cement, the chemistry is extremely complex, and not completely understood. So at the highly technical level, the details not understood. I'm trying to imagine our politicians getting their minds around this. It's an almost impossible task, I would suggest.
I think once people see that it is being used, and not just in old Roman buildings, but Brisbane Airport using it for structural purposes, being used for different structural purposes around the world. I think once people see that, people will be more relaxed about it. But the chemistry of cement is complicated, and of these geopolymer cements even more complicated, I believe.
I'm sorry, I missed the point, I suppose. What can't the CO2 from cement production be captured and stored?
Well, it could in theory be captured and stored, but I don't really believe in carbon capture and storage as an answer to much. You're just adding to the costs of existing things. It doesn't really feel like a sustainable way forward, and you have to have. It's hard enough with a coal-fired power station, which is producing masses and masses of it, but there are cement plants all over the place. They're not all big, and each one has to have a carbon capture and storage facility. It just seems unlikely. BZE's got a report on carbon capture and storage. which basically says let's try and find another way.
That's probably we need to put it back in the soil and also to grow plants with it.
Carbon dioxide.
Yes.
Yeah, well, you can't just put it in the soil; it'll just come out.
Well, we grow plants with it.
Ah, right. Yeah. Okay. Yep.
Well, at what point is the CO2 released in the process? Is it where it's actually being mixed, or is it in the production of the cement product?
It's the production of the cement product. So it's when you're converting the limestone into lime. Right. Yeah. So that reaction is going on. Yeah. I think maybe when you're mixing it, there's subsequent reactions like that. But the bulk of it is when it's in the cement plant.
Right.
Yeah.
Michael, if the setting of the cement, in part at least, is the reverse of that reaction, presumably some of it is taken up. I mean, I've often wondered, big block of concrete that you've just made.
Yeah.
The permeability of that, it must be more than just the reverse of that production of calcium oxide.
Yeah.
The reverse of that. I can imagine that the diffusion resistance into a great block of concrete is such that dependency on reuptake of the carbon dioxide is fraught with difficulty. It must be a complex reaction. Must be.
You're talking about the cement we're using today?
Say Portland cement,
yeah. I think when cement sets, when concrete sets, it is absorbing carbon dioxide, but what the quantities of that are compared to this, I don't know, but it's obviously quite small, because I've never read anything saying that, it offsets it.
No.
Yeah, a lot of the detail of what I'm showing you tonight still has to be worked out, I have to say, but we'll get there.
So a strategy for geoformers would be to identify the high volume and low risk applications for those technologies, so low rise, prefabricated cast concrete, that sort of stuff.
Yeah, possibly. Although from what I've told, the strength of concrete is just like Portland cement.
But I think Portland cement is more reliable in that the ratio, the ingredients, if they're mixed in slightly off ratios, Portland cement doesn't compromise the strength, whereas some of the geoformers, it's a little bit more sensitive to accurate mixing.
Yeah, I think you're right. Actually, it is a little bit more sensitive.
So high rise, I think that would be a risk, a barrier to the technology. Where I think you're talking high rise volumes, relatively small compared to large volume low rise.
Yeah. I mean, I need to discuss these things with the guy I mentioned. But yeah. I'm hoping to talk to him tomorrow, actually. Yeah, did you have a question?
Yeah, I was just, going to make a statement. It doesn't seem like there's any incentive for you to take this up.
Yeah.
Unless it's actually cheaper.
Yeah.
And just as good.
Yeah.
Or we get to the point where the price on carbon or some other reason coming from government why they push this hard.
Yeah. As far as I know, I'm trying to get to the bottom of the cost. I don't think it is cheaper, but that's a problem with all of this. I mean, it'd be more of a problem when I get onto steel. We're writing this report for a world that takes low carbon, the Paris objective seriously, and in that world where governments actually say, we've said we're going to aim for 1.5 degree rise, they'll have to implement these things, and once there's political will, cost isn't discussed anymore. Yeah, but you're right. I'm not suggesting these things have a market, advantage.
I was going to say the research can be done so that they finally decide they want to do it.
That's right. All right, let's get on to steel. So steel, iron's made from iron ore. So the process on the right is how it's normally made. So you often hear steel's about 5% of world emissions, so it's a big chunk, like cement. For every ton of steel made, I think there's about 3 tons of CO2 produced. So iron ore is basically iron oxide, iron and oxygen. You need to reduce, as someone suggested, you need to reduce that iron and oxide, so take the oxygen away from the iron, which is very energy intensive. That's done with coke, and you often hear politicians say, when they're defending the coal industry, oh, well, you can't make steel without coal, you can't make a wind turbine without coal. I'm hoping that's not true, but we pretty much don't make the steel without coal. So the blast furnace on the right, coke and iron ore pellets is put in at the top, and superheated air and oxygen is put in at the bottom, and it essentially heats it up to 1700 degrees. The iron ore is reduced. You get iron at the bottom of the blast furnace, and you get CO2 as a byproduct. So the coke is playing several roles. It's providing energy, it's providing the necessary chemical reaction that leaves purer iron, and it also plays a sort of structural role in the blast furnace. It needs to be porous but also strong enough, because that blast furnace is kind of packed up and it takes a while for the iron ore several hours to make its way down the blast furnace. So that's why coke, made from coking coal, which is just a high carbon, fairly pure form of coal, is vital to the steel industry. When you use a blast furnace, the iron you get out at the end has still got too much carbon in it, the iron from blast furnace. So you put it into this thing, bottom right, basic oxygen furnace, and basically blast oxygen at it at high temperature till and get out the rest of the carbon. That is also obviously producing carbon dioxide. So again, if we're going to make steel that way, and carbon capture and storage is the only way to make it carbon neutral. There's another way of making iron, which is direct reduction, which is done with natural gas, where you don't need such a high temperature, it's lower energy. It produces something called sponge iron, so a slightly less pure form of iron from the iron ore. It's a bit more similar to what in the Iron Age, the way they were making iron when they just put iron ore on fires. So that's done with natural gas, and the reduction of the iron ore is both by the carbon in the natural gas and by the hydrogen. So that's a kind of a clue to the way I'm planning to go with this. But anyway, the kind of ways people have looked at CO2 reduction in steel manufacture are top gas recycling, which just is a way of making the process more efficient and reduces the emissions a bit. High sauna, which is something Rio Tinto looked at. It's a non-blast furnace way of producing iron. The main advantage is that it produces a pure form, a pure stream of CO2, or pure-ish. So there used to be a plant near Perth, which is now being dismantled and is being rebuilt in China. So if we wanted to do CCS, it would be with a high sauna smelter, it's called. Direct reduction with hydrogen. Biomass with or without CCS. So BlueScope have done quite a bit of research into biomass, and they have identified a tree that grows widely in southeastern Australia. They won't tell me what it is, but I think it might be mallygums, which is really suitable for using in a blast furnace instead of coke. And when there was a carbon price, BlueScope were pretty interested in that. And if you used it with CCS, it would potentially be carbon negative. But on the bit, you would need a lot of trees. So I've seen a study about the UK, which produces some steel, I think maybe about the same amount as Australia, perhaps a bit more. If they used biomass to produce steel in the UK, half of the UK would have to be forested and harvested. So obviously Australia is a lot bigger than the UK, but it does just show you how many forests you need.
And they can't make into those trees are grown.
That's right. Yeah. So you could make steel with electrolysis. I think someone's made about 100 grams in a lab. So aluminium and some other metals are made with electrolysis. So you could do it with that, but it's inevitably going to be a low volume way of making steel. It's a long way off production. So the way I'm looking at it at the moment is direct reduction with pure hydrogen. So at the moment it's done with natural gas. Some of those plants that use natural gas extract hydrogen from the process and put it back through. So it's actually already working with more than 50% hydrogen. So I don't see any reason why they can't just make it with pure hydrogen. This is what the basic chemistry would be then. Iron ore pellets plus hydrogen, you would just get out your sponge iron and water. So no carbon dioxide, it would be waste product and water. So as I say, plants close to this are already done. The sponge iron would go in an electric arc furnace. So most steel is recycled in the world already, and it's recycled in an electric arc furnace, which is, as the name suggests, electricity is the dominant energy use in an electric arc furnace. So what would come out of this would be chucked into one of those, so that could be supplied with renewable energy. Some companies in Sweden are getting together and are building a pilot plant and have a 20-year plan to build a steel plant that uses direct reduction in hydrogen. So they're interested in it, and this is the way at the moment I think we're going to pursue. And I've been talking to Rio Tinto, and I was worried to a guy who's been working in steel for 30 years and knows everything about the steel manufacturing process, and I was worried he was going to tell me there was some massive barrier to this and that I was crazy, but he's quite excited about it and said, no, you could do it like that. Let's look into it.
And presumably the hydrogen, if you're going to avoid extracting natural gas and splitting the hydrogen out, presumably you produce that hydrogen ultimately from electrolysis out of water.
Yeah.
And just water and electricity. So the whole system goes back to electricity.
Yeah.
In this electric planet which was now built.
The electric planet, that's right. So to be honest, that is one of the problems, because you would need huge amounts of hydrogen. You don't have the problem where you're transporting hydrogen. People probably know hydrogen's hard to transport, likes to escape, because you could manufacture the hydrogen at the steel plant, but as you say, with electrolysis and water. So that's what they're planning to do in Sweden. But you need huge amounts of hydrogen, you need huge amounts of electricity, but the benefit of it is that you can use that electricity whenever. So there's a small hydrogen plant just being set up in Canberra at the moment, and they have developed a system. Most industrial processes just need to run continuously, but they've developed a process where it can just turn on and off, makes hydrogen from water, and just uses the electricity when electricity is cheap. So that's if we had a 100% renewable system, we'd have lots of times when we produce more electricity than we're actually needed. So that could be used to produce hydrogen.
So it would be connected to hydro, wouldn't it?
Hydropower?
Hydro?
Are you talking about hydropower?
Hydropower, yeah.
Oh, whatever.
Anyway, yeah.
Just electricity. Yeah.
I thought, Michael, I read somewhere the Japanese were doing with their hydrogen fuel cells. They were doing something about water, because it's one natural resource they've got abundance of, surrounded by water.
Yeah.
So I can't recall the reference, but there may be something there. Now, didn't Mazda do something about sponge iron and got into a lot of trouble? because they didn't purify it enough. They were recycling steel out of the automotive vehicles.
Yeah.
And they didn't purify it enough, put it in new vehicles, all of that.
Yeah.
And they weren't, the steel wasn't perfect, there was impurities.
Oh, yeah.
They went through a phase, and that's why they had to sell down quite a significant shareholding to Ford.
Right. You might be right. I didn't know about that, but
maybe worth looking at.
I don't think there's a problem with the process of using sponge iron and electric arc furnace, because the company that produces steel at the moment with direct reduction, this plant I'm talking about, it uses natural gas but a high percentage of hydrogen. They actually did that to produce a higher quality of steel.
But just look at them.
Yeah.
Find out the master one.
Yeah.
They all of a sudden went from a very good quality vehicle.
Yeah.
They were probably the best in mass-produced vehicles.
Yeah.
In Japan. And all of a sudden their quality problems hit them. And it was at the time they were recycling they were knocking down their engines, old engines. Their steel bodies.
That sounds like it might not have involved sponge iron, but they're recycling of steel's always recycled in an electric arc furnace. So it sounds like
going through the process.
Yes. Yeah. All steel in the world is recycled with an electric arc furnace. Yeah.
There may be stuff there in that area.
Yep. The other kind of challenge with this route is that it works best with magnetite, so the iron ore that's magnetite, which isn't what Australia is abundant in. That's one reason why Sweden are looking at this, because there's lots of iron ore in Sweden and it happens to be magnetite. So for reasons I don't yet understand, it would be more challenging to do it with hematite, but not impossible. So I got a couple of people thinking about how you do it with hematite.
But South Australia is full of magnetite.
Right, is it? Yeah.
So anything basically tropical Capricorn below steel is magnetite.
Oh, that's good to know. I don't know.
You've got it all the way across to the Western Australian coast.
All right, so plenty of magnetite. All right. We've cracked that one then.
I keep saying,
it
sounds like this is a case to go and chat about Mr. Pine's shoulder. Pine, say, look,
did you say the shoulder or the head?
Don't be like But, we're going to resurrect the South Australian economy because you've got plenty of sunshine, plenty of wind and plenty of water, plenty of magnetite.
No, I think you're right.
Not enough voters.
Any other views or questions on steel?
What happened to magnesium in Western Victoria?
What happened?
There's supposedly massive quantities.
Right.
They were going to develop as a material industry, but I've not heard much about it.
Yeah, I'm not sure.
Doing research on it, this is years ago.
Yeah.
It's lightweight, high quality metal.
I don't know.
Maybe they ran into technical problems.
Maybe they did, yeah.
The dry magnesium fell over because the plant was built in Queensland and didn't work. Spent $400 million on it. So they're still doing some background work.
There is an active magnetite mine in South Australia, in the peninsula called Centrex.
Okay.
And it's quite huge resource.
Okay, that's good to know.
It's controlled by the old St. Petersburg boys of Adelaide.
Right.
So where are the transport costs calculated into this process?
The transport costs of?
Shipping iron ore from here to Japan or China.
Well, this is about making steel in Australia. So where the transport costs of shipping the steel overseas? That's not really part of this project. No. I mean, that'd be insignificant compared to making the steel. I won't say insignificant, but small. So the last chapter is using less, which is these are some of the ways of using less. So it's kind of conceptually the most difficult chapter because there's lots of different ways, and BZE is usually about, you know, we do one thing, we use electricity, let's just apply a technology to what we do, and you know, that'll solve our problems. Whereas using less, you're getting into the technology, you get into areas of, you know, our throwaway society and the fact that we have a fridge with a faulty rubber seal, so we chuck away the fridge, and you know, more fundamental issues with capitalism, which I'm kind of want to avoid really in our report because it could be never ending. So I'm going to have to focus in on some areas. So you could use less by design, so I'll show a picture of what I mean by that in a second, but a lot of things are designed in a way that they could be designed with less of the material in them. There's a lot of yield losses in making, say, metals, and while that's all recycled, it's energy intensive to recycle it. Reusing directly, so you know, if you have at the moment a steel beam, for example, from a building's dismantled, the steel beam is more than likely going to be melted down, put in an electric arc furnace, and made into steel again. Whereas there's probably nothing wrong with the steel beam in the first place. It could just be reused. Longer life products, so yeah, designing everything to last longer so you don't have to replace them, and lots of ways of reducing final demand. So shared ownership, people are talking a lot these days about, you know, car sharing, and driverless cars would be shared, so that those cars would be used a lot more efficiently than today's cars, for example. Alternative ways of delivering service, so again, a transport example, video conferencing, if it never seems to have actually replaced any business travel, but certainly could. And alternative materials, which is definitely something we'll look at in this report. So replace a high emissions material with an alternative one. I'll show an example of that in a minute. But this is what I mean by that first one, using less by design. So nearly all steel beams look like the one on that side of the screen. But there are lots of ways you could make a steel beam which did the same job in a building that contained less steel. And the reason this isn't done is because the benefits of optimizing a simple shape and only ever making one shape outweigh the cost of a bit of extra steel, which doesn't cost that much by comparison. And loads of examples of this. You know, all products are optimized for speed and ease of production rather than using less of them. Well, most products anyway. So that's one example of using less by design. Alternative materials. What's this? Where's this building? Does anyone recognise it? It's a 10-storey, I think, apartment building in Docklands, and it's made from timber. Yeah, cross-laminated timber. So this is what who was talking about that earlier? Yeah. So this is a 10-storey one. I think the tallest in the world is 20-storey. And there's hardly any steel or concrete in this building. So they've quantified what the emission saving was from that, so there's a pretty big emission saving. The cross-laminated timber has great thermal properties, actually better than concrete. It's also more fire resistant than concrete, which sounds crazy, but it is. Most of this was built in a factory, so it's modular design. It's just assembled like a 3D jigsaw on site. So there are loads of advantages of this, and it's an industry in its infancy, but I think it has huge potential. There's so much of our steel and concrete in particular just goes into buildings.
What's it cost?
I'm not actually sure what it costs. Yeah. You're saving a lot on the construction. Yeah. But yeah, I don't know. Yeah.
How did it go for energy efficiency?
Good for energy efficiency. So this is a Green Star. I think it was the first Green Star 5 building, apartment building in Australia. So it's got good energy efficiency. Yeah. The thermal properties of the timber, as I say, are higher than concrete. So good. Obviously the mass is less than concrete, but the thermal resistance is better than.
It's been extensively used in Japan and Wellington because it's earthquake proof as well.
Right, okay. Yeah, I knew Japan was one of the countries, and some of the Scandinavian countries.
And there was a good program on Grand Designs where they put a $400,000 house up in 5 days. It took them a month then to finish it off.
Yeah. I mean, just from a cost point of view, it amazes me that modular design and building most of the building in a factory hasn't taken off more. I think in Scandinavian countries it's the normal way houses are built now, but why it isn't everywhere, I don't know.
Is that because of the lack of economies of scale? You haven't enough orders going.
Yeah, maybe it is. Yeah.
Now I remember that. I think that became worthwhile when we had a carbon tax.
Right.
And it was a lower cost because of the carbon tax.
Yeah.
So, but I remember reading the report on it.
They're pretty high-end apartments,
Yeah.
I mean, obviously in Docklands, they were being sold for a lot. Might be less worthwhile in some other places, but yeah, I think this is one thing we'll definitely include in the report for using less. But how much of these other areas to include? Because this could be massive. I mean, I don't know whether you've heard people talk about the circular economy, in which you design everything to be reused and there's no waste. But that has to be part of the design and producer responsibility. Just that is a massive area, and I'm kind of reluctant to get into it too much. So we may focus on certain areas of using less.
What would be the impact on forests of a big
well, it would have to be from managed forests. Lots of managed forests at the moment. Yeah, but it is a good point. How much land would be needed to provide the timber needed for buildings?
What timber is used?
Sorry?
What timber is used?
Do you know, I don't actually know what species are used, but it's cross-laminated timber, which is a relatively new technology. So it's lots of layers of timber products that provide incredible strength and the other properties you were talking about.
You can use virtually any timber, and the other beauty is that you don't have to prune your trees because the knots and things, because they're cross-laminated and they don't fill. And the other thing is they are at least inch thick boards, so it's not like plywood or other, which you have to have in thin sheets. So you can saw up any timber, and one of the other advantages of it is you can make it into a continuous process. So a log goes in, it's cut up into features, it goes through microwave, and the microwave dries it, and then you go straight on to cross-lamination. So you can have a continuous process with using virtually anything that can be cut up into suitable size.
Well, that's good to hear, because the continuous process will make it more efficient. And I'm also glad to hear that because I don't know how it's produced, that microwaves are used to dry it, because that's obviously also electrical. So the electrification's already been done.
It's probably an opportunity to use waste wood as well.
I think they use the microwaves to get rid of fungi.
Right.
My memory is the Carpet Farming Initiative had a big report on it. That's why, as soon as you mentioned it, I was going, because they were calling its features out, because here they were saying it's an industrial process benefiting from a carbon tax. But that's going back about 4 years, 5 years, and I'm not sure this government's taken it down before.
Probably not. We're going to get some help on this for people who were part of there was a CRC on sustainable buildings. So I was over in Perth 10 days ago. So people know Peter Newman, and famous guy in sustainability, and his team. They're going to help us with this area on things like life cycle analysis and things like that.
You mentioned a bit earlier that the cross-laminated timber was more fire resistant than concrete. Can you be able to tell me basically why?
No. There's people over here seem to know the answer to those sorts of questions.
Because what happens is it chars on the outside, and char is a very good insulator. So, and then they have a fire retardant built into the glue.
Yeah.
And so as it chars, it's insulated, and then as the heat penetrates, it releases the fire retardant.
Well, thanks for helping me out on that one. So that's one alternative material we'll talk about. There's another one. By the way, what do people think is the steel product in the world? What steel product is the most common in the world? Uses most steel? Single kind of use. Yes, well done. I was amazed to hear that. Yeah. So nearly 20% of world steel goes into reinforcing concrete.
There's an interesting thing about concrete. China in the last 3 years has made as much cement as America did in the previous 100 years.
Yeah, I've seen that statistic. I still find it quite hard to believe. But apparently,
John Brumby stated that at a...
Yeah, well, if he said it, I won't challenge it. If it came from a politician, it must be true. So there are a few possibilities for replacing steel reinforcement. Concrete needs to be reinforced with something to give it the tensile strength. And one of them that I found quite interesting is basalt reinforced concrete. So you make a kind of polymer with the main ingredient of which is basalt rock. Mixed with glass and plastic, and that's actually used in some situations at the moment where the concrete is going to be in a marine environment, for example, because the steel reinforcement will rust pretty quickly in a marine environment, whereas the basalt one won't. But there's a few other things like plastics. There's even organic materials that you could use to strengthen concrete. So that's another thing that will go into the report once we're happy with it. But one problem with basalt is that its melting point is almost as high as steel. So you have to melt the basalt first. So it's pretty energy intensive, but I think it's better than steel.
Does it have tensile strength, the basalt? I mean, my crude understanding of the reason for putting Rio in concrete is that it can tolerate the tension.
That's right, yeah.
So the concrete is very good under compression.
Yeah.
And visualising, what you're talking about is lava, the stuff that's covered all our Western District and so on.
Yeah.
And I understand huge areas of India that they're getting.
Yeah.
But it's hard to visualise it. It's in a sense, it's a glassy like material, and glass. I wouldn't think is. I guess when you think of glass product.
I have to admit, it's hard to see why basalt would provide tensile strength, but they have developed a basalt. It's not pure basalt, it's mixed with carbon and plastics and other things that apparently does work very well.
It's used in the composite industry. It's similar to fiberglass.
Okay.
It works, if you look up as fiberglass suppliers that deal in high end, they'll have carbon, Kevlar, basalt, E-glass, S-glass, fiberglass.
Yeah.
So I think it's the process of spinning it into fibres and then creating that. So like the same as fiberglass.
Yeah, okay. Yeah, so there you go. There's a lot of processing that happens to the basalt before it can be used. Sorry?
Not rocks.
No, not rocks.
One thing on the materials, I'm sure you're aware of Bill McDonald working cradle to cradle. He was talking to not go down too much of that circular economy.
Yeah.
But I think there's some points in there in terms of what they identify risks of efficiency, where you can, when you make a process more efficient, you can create growth.
Yeah.
So you can in effect make the process more efficient, so it's using less, but that creates a step change in the demand. So by increases in volume, you actually go backwards. And I think design for demanufacture, and there's quite a bit in that cradle to cradle philosophy, which may have relevance in terms of some of the other issues that are not so obvious.
Yeah, I think you're right. I think it might, and I haven't discounted it. I was just saying I'm nervous about it becoming this massive thing. Whereas BZE reports tend to be about technological solutions. But part of the solution to industrial materials is using less.
Agreed.
Yeah.
I just think there may be a place where not going not overboard, but just referencing the potential for runaway, increases in production resulting from efficiencies. And if they're not fundamentally right, then we can end up going backwards inadvertently.
Yeah, you're right.
10 minutes, Mike.
10 minutes, okay. Well, I haven't got a lot more to the presentation, but I can't remember if I said we'll probably publish this in several reports. So we might start with once I can get back to dedicating myself to this, when we have a new CEO. We might start on steel and produce a steel report, and then a cement report, and then a renewable heat report, whatever order it is, and then finally an industrial processes plan. Has anyone else got any more ideas on how we could tackle the using less chapter?
Mark, you looked at 3D printing.
I saw a video online of a steel bridge being made in Amsterdam with a 3D printing robot, and it was being made in situ over one of the narrow canals in Amsterdam, and it was making this intricate steel bridge, and I was thinking there's not a bit of wasted steel in that process. Every little bit of steel is going into the bridge, and so I thought, is there a...
So one of the great successes was a bloke who graduated from RMIT.
Yeah.
And he was a petrol head. Went to knock on the door, I think it was McLaren Williams.
Yeah.
I got a job.
Yeah.
Became the expert on the heat transfer in Formula 1.
Okay.
And then all of a sudden he hit upon 3D printing the heat transfer pump.
Yep.
And it's 1/3 of the size of the old standard pump. And that was both in terms of weight.
Yep.
He could print it in the garage if something went wrong while they were flying around the Formula 1 track.
Yep.
But it was this, and it was, he designed a completely different product because he was able to manufacture it in 3D printing. And it was 1/3 of the size. That was the biggest. And of course that was significantly more efficient. And he could literally, while they were running the practice and they had a problem, but he just got press a button and 30 minutes later he had a brand new one.
Yeah.
And it seemed to me that straight out of that 3D printing is going to have a monstrous effect on manufacturing.
Yeah.
But also on import. So providing you've got the necessary raw material, rather than shipping it across from China, you have a 3D printer here.
Yeah, it's got so much potential. It kind of makes my head hurt to think where the world will go with 3D printing.
And I suspect that might be a second thought.
Yes. So what I thought after my 10 minutes of consideration about 3D printing was that at the moment it's used for those very specific products at the moment. So you were talking about Formula 1, it's used for medical tools, so they're not using huge amounts of material, whereas with this we've got to tackle products that are using the bulk of the world's material.
The point of the bloke is that previously they used a huge amount of material.
Yes.
He's done an IPO in the States, and I think it jumped to almost $1 billion immediately in value of the company because of literally that. He's in Silicon Valley.
There's a company in China that's 3D printing 2-story houses. That's right into ours.
Yeah, I did hear about that as well.
And they're going to stop using cement, not because of the environmental reasons. They're going to start using new polymer because of the wear and tear on the machinery. So they found they actually get better life out of the machine with polymer construction.
And very little waste. Yeah, well, we might include 3D printing. Andrew.
Very brief. How much last year, and the steel emerges from concrete in spots, and of course rusty steel expands and breaks the concrete.
Yeah.
So these different reinforcements would have great potential because they have great houses, would have greater durability.
Yeah, that's right. Yeah, that's one of the advantages of basalt reinforcement. Yeah, as I said, it's used in marine environments for that purpose at the moment. But eventually, steel will rust. Steel reinforcement will rust. Yeah. Yeah.
So the other thing, just in terms of using less, packaging to me is an extremely wasteful activity.
Yeah.
It could be much better done.
Yeah.
And the other thing that I was thinking is materials, combining of materials so they can be separated at end of use.
Yeah.
And I think this is something. It's a subject we just have to touch on because it could be massive.
Yeah. Well, this is all part of the circular economy, isn't it? That
Right.
everything's designed to be reused, and one of the things stopping that at the moment is that different alloys are mixed up, different plastics.
And one of the things that I'm continuously amazed is that you can go to the School of Architecture and say you've ever built McDonald, and people say no.
Yeah.
And that stuff's been around for a very long time.
Yeah. Surprisingly.
Schools and that sort of stuff. Are they thinking about designing for demanufacture, remanufacture? I think part of the problem is that those messages haven't actually been targeted at the right people.
Yeah.
And I think, if it's put forward in this forum, it's an additional way of getting there.
Yeah.
And you guys have great links to academia.
Yep.
So even though it's been done perhaps before and you may not do it comprehensively, I think it's maybe from a strategy point of view.
Raising awareness.
Correct.
Yep. That's a good point. Thanks. Yep. All right.
In one of your early slides where you had concrete and steel, you had other, which I think was 30-something%.
Yeah.
A lot of those things, even though they're not the way industry, there's only a huge number of things using low level heat for part of the process. Wouldn't there be some scope there to do some investigation more generically?
Yeah. So that's what I'm trying to tackle with the renewable energy chapter. So most of those are not process emissions. So the process emissions, as far as I'm aware, come mostly from, so the non-heat related greenhouse gas emissions come from steel, cement and refrigerants.
Yeah.
So most of those, they're creating emissions just because you need heat. So that's what I'm trying to tackle with the renewable heat chapter.
Okay.
Yeah.
Okay.
Yeah.
Suggestion you're asking additional chapter.
Yeah.
I think it'd be worthwhile doing a chapter on the whole calculation method. So activity-based costing gives you whole of life, right, and it ignores or can ignore the usual annual costing way, but it puts in all your drivers, and the beauty is that you plug in your emission costs, your carbon costs, and so you can get your whole lifetime from beginning to end, from the beginning of design, a gleam in the eye of the designer right through to the final decommissioning and recycling.
So life cycle analysis.
Yeah. So having even as an appendix so that people can actually use it, because many of the techniques that are used leave out externalities, leave out all of these other, and I went to a talk on carbon capture and storage the other day, and you'd left out all the externalities.
Yeah. I'm a little bit frightened by life cycle analysis, but thank you. Okay, go on.
Look, if you want something, just an idea, this is
Yep, I'm interested in ideas,
about using less by design. One thing that strikes me is that if you've got a large plant that produces steel, it seems to be about all it does. And if you've got a large plant that produces cement, that's about all it does. You've got all of these industries around the place, and just over the chain of wire fence, it's a totally different industry, and it's producing a different product and using its own heat and all the rest of it. Probably one good area for some really detailed research might be how do they amalgamate two industries into one building so that they can actually share the heat? Like you've got steel production that takes 1600 C, and then you've got some other industry that only needs 800 or whatever. Is there a way that these two industries via the one building can share the heat to get increased efficiency out of it? And I'm quite sure that there are ideas that we've never even thought of yet.
Yeah, I think that's a good idea. We'll see if we can find room for it in the report, but I know in European countries, there's Denmark and Holland, where they're really interested in the circular economy. They're starting to talk about things like that co-location of industries that can, be beneficial to each other. I think we've got time for one more question. One more quick one.
Just on the ABC Science Show a couple of weeks ago, they were talking about geothermal. And they're saying how the Latrobe Valley is actually a really exceptionally good geothermal hotspot because the coal is a blanket. And you've only got to go down 500 metres instead of 5 kilometres to get to 70 degrees. And they're saying that as an input into the process of generating power, that would be massive savings if they could feed the water in at 70 degrees. I'm wondering whether some of these other processes could use something similar if you start at a higher base.
Yeah, you're right.
The temperature.
So is it hot water or just hot rocks?
Well, hot rocks and hard
they'd have to pump water. Okay, well, all right, might look into that then. Yeah, especially if it's in the Latrobe Valley.
On the sunshine.
Yeah, okay, all right. Thanks for that.
All right, thank you very much, Michael.
Thanks, Mike.
Okay, Michael's moved to go into the pub down the road and continue the discussion. If you do want to continue the discussion, please take it outside the room so the security guard can come and lock up without getting grumpy. I'll just walk down the ramp outside the building, and the pub is just on the right before the first set of traffic lights. BZD is supported by what we call baseload supporters. John's just going out rattling the tin. But a baseload supporter is a person who gives to BZD, say, monthly. All of BZD's financial support comes from individual donations like that and not from industry or politics. So it means that we can remain independent and tell things like they are. So if you like the idea of BZD and you're able to support us, that would be very welcome. You can catch up with the discussion group YouTube recordings and download slides at the BZD website, which is bzd.org.au/events. The next discussion group is on Monday the 5th of December. It'll be here, and at this stage the speaker is a secret, so stay tuned.